today. I don't know why she didn't announce.
All right, well. Get started, I suppose. Tonight, we want to extend what we were doing last time, right? If we can make integrals a lot easier through coordinate transformation of cylindrical and spherical coordinates, maybe we can do even better if we can do more general coordinate systems. Let's see if I can get this to zoom in here just a little bit. That's tonight's topic, is looking at general coordinate transformations. Not absolutely general, but much more general. And subtitle, we could say the Jacobian. That's the key to be able to do this. Named after famous mathematician Jacobi, who we butchered his name, call it Jacobi now, usually. If you've been in linear algebra, maybe you've seen the Jacobian before. And again, the idea is to make your integrals easier, right? When you get triple integrals, integrals of integrals of integrals, pretty soon you typically get something you don't know how to find an antiderivative of. So suppose we have this. Consider a map that is a function. Right, a function is a rule to each input in a given set called the domain, assigns exactly one output. We can make a map like this. Let x be some function x of uv, and y be a function of u and v. And we can transform a portion of the xy plane and the uv plane back and forth doing this. And so you give me any uv, I can give you out the xy that corresponds to it. This corresponds to a change of variables in the uv space and xy space. And maybe I have some region R, not necessarily a rectangle, but I'll draw it that way, in xy space upon which I want to do some integration. And then I have some other space over here, S, with appropriate changes of variables. We can make each point u0, v0 in this space as the output of these two functions. Give us out a point x of u0, v0, y of u0, v0. And so this is a map from a point, from points here to plane points here. We can call it phi or something, in which case then we say consider a map or a function phi that you input a point in the plane and get out a point in the plane. So it's a function. It's just giving you the two coordinates instead of one. And if it takes the points in here and maps them onto the points over here in a nice way, then we can transform our integrals. For integration purposes, and so here the domain would be S, and it maps S into R. So it's a map phi taking the region S, some region S in UV space into a region R in XY space. We'll write it that way. It's a function. Where it's given by some functions here. For these, we need to introduce, and after Jacobi, the Jacobian, which we sometimes denote J. That's a nice short letter for it. Another way to write it is this popular notation, dxy duv. What does that look like? Yeah, it looks like the partial derivative. It looks like it's supposed to remind you also, and that's part of it, of the u substitution formula, where you have dx du du. If this would be the dx du. This is defined to be the determinant dx du dx dv dy du dy dv. So this is a definition, and these two are just two different notations for that. And I don't know if everybody's seen a lot of determinants before, so I'll just remind you where the determinant of four numbers A, B, C, D is defined to be the number A times D minus B times C. So that's the determinant. It's a linear algebra concept that we need here also. And the Jacobian is going to tell us exactly how to transform integrals. All right, so here's the example.
It was called determinants again.
Yeah. So it's called the 2x2 determinant of the array or matrix of numbers C, D of numbers. All right, so I first need to introduce the determinant. If I give you this determinant, 3 minus 5, 2, 7, I just put four numbers into this box. What that means is just take 3 times 7, this diagonal, and subtract 2 times minus 5. So 21 plus 10 is 31. So the determinant of this matrix is 10. So I should say, I should give the official term of the matrix, which is a rectangular array of numbers. And this refers to it having 2 rows and 2 columns when I say it's a 2x2 determinant. All right. So that's 2x2 determinant. Just take this times this minus this times this. And why is that convenient to define? It shows up in just a little bit. Yes or no? So now, what's the Jacobian of a transformation of coordinates? Here's a real example of a transformation of coordinates. Suppose I put x equals u cosine v and y equals u sine v. Right? This is x equals a function of u and v. You can call this x of u v if you like. And this is a function of u and v, y of u v. What does that remind you of? U cosine v and u sine v. You just put r and theta instead of polar coordinates, right? So this is a transformation between polar and rectangular coordinates. I wonder what the Jacobian is for that one, right? The Jacobian is a determinant call it equation one, I guess. Star is, I should really call this one one. That's the important one, the Jacobian. The Jacobian for star is what? Well, we take J is dx du is du cosine v du dx dv. Du cosine v dv. And then partial of y with respect to u is du sine v du. Partial of y with respect to v is du sine v. dv according to star is the Jacobian. And now you take these partial derivatives. Derivative of u times constant, right? It's just a constant cosine v, treating v as a constant. Partial of u cosine v with respect to v. Now u is treated as a constant. Derivative of cosine v is minus sine v. So you get minus u sine v. Take derivative of u sine v with respect to u. Well, it's just sine v. Partial derivative of u sine v with respect to v. Derivative of sine is cosine, so you get u cosine v. The determinant means take this times this minus this times this. And I get cosine times u cosine is u. Well, let's write it out. So according to the formula for determinants, it's cosine v, this one times this one, u cosine v, minus this one times this one, sine v times u sine v. And let's see, this comes out to be u times cosine squared v plus u times sine squared v. Oh, it just comes out to be u. So this is a pretty simple result. If this had been written r cosine theta and r sine theta, this would come out to be r. Precisely the transformation letter that you have in transforming your integrals. In other words, if you have a double integral of f of x y with respect to x and y, you can rewrite it as a function of r cosine theta and r sine theta, and replace the dx dy with r dr d theta. That r is actually coming from the Jacobian, it turns out. So we'll point that out as we go along. But there's where the Jacobian comes in. It's the transformation. So there's the transformation for polar coordinates. We find out the Jacobian comes out to be u or r. Suppose we make a different kind of transformation. This is actually a really important one because of polar coordinates, but these are very important too. Suppose I have x equals let's say AU plus BV, y equals CU plus DV, where A, B, C, and D are numbers. And U and V are the variables. Now what's the determinant? The Jacobian. The Jacobian is actually constant. The Jacobian is just a determinant, partial of AU with respect to U, partial of, it's AU plus BV. Partial of AU plus BV with respect to V, partial of CU plus DV with respect to U, partial of CU plus. Now what we get is just A, B, C, D. This becomes AD minus BC. How can that be significant? this is actually the magnification factor between the u and v coordinates. In other words, if I take a region in the UV plane, let's see if I can say this better. If I take the interval from 0 to 1 and 0 to 1, so it's a 1 by 1 square, right? And suppose I want to transform it under this mapping phi from this region S here, the square, into a region here in the XY plane. What do I get? Because this is what's called a linear transformation, a number times u plus a number times v, a number times u plus a number times v. This is called a linear transformation. And this is what happens.
Can you scoot the camera a little bit to the right?
Oh, okay, I'm sorry. Yeah, I'm not putting that over far enough, am I? There we go. I think that's good. And what a linear transformation does is it takes lines to lines. It's not too hard for us to show that. If you take a line y equals mx plus b and you, or line in the UV plane, v equals a number times u plus a number, and rewrite x and y in terms of that, you find out that y is equal to a number times x plus a number, and so it takes lines to lines. And what happens then is you can just take the four corners of this box and plot them over and see where they plot in this plane. So if I take 0, 0, in these linear transformations, the origin is always mapped to the origin, right? C times 0 plus D times 0, A times 0 plus Z, B times 0 gives you X and Y equals 0, 0. So this point, the origin maps to itself. Now the other points are different. The point 1, 0, for instance, I get A times 1 plus B times 0, C times 1 plus B times 0. I get the point AC. So I get some point here, AC is this one. And then if I take this one, 0, 1, then I get 0B and 0D. 0 plus B and 0 plus D, I get the point BD. And so this line segment here, like this vector here and this vector here, plot to this vector here and this vector here. And now maybe you remember if you these two sides will plot actually the parallel vectors by the same token. And what happens is parallelograms in this space, because parallel lines map to parallel lines, will map to parallelogram lines in this space. I'm leaving a little bit of stuff out of here. This did not waste time on the geometry. But any parallelogram over here, including rectangles, will map to a parallelogram over here. And then you ask, what's the area of the parallelogram? The formula is precisely this AD minus BC. You can show that with the cross product, actually. And so the region R has this magnification factor, AD minus BC, precisely what the Jacobian is. So the Jacobian is the magnification factor to map these rectangles that we did for adding up integrals in this plane into parallelograms that we want to add up in this plane in the XY space. Consequently, it leads to the following wonderful theorem. Maybe I should do one more example on that. In the case that x equals u minus 2v and y equals 3u plus v, what is the Jacobian? The Jacobian is just partial of this respect to u is 1, partial of this respect to v is minus 2, partial of this respect to u is 3, partial of this one with respect to v is 1. You get this for the Jacobian, and then you take this times this, 1 times 1, minus this times this, 3 times minus 2, 1 minus minus 6 gives you 7. Is the Jacobian here, and that's the magnification factor between the two things. Now, I said that Jacobian is the magnification factor. It actually can come out to be negative, and so the absolute value of the Jacobian is the magnification factor. But for these linear transformations, you just get a constant magnification. Every square over here gets mapped into a parallelogram over here that's scaled by the absolute value of this number for its area. And so you can, instead of adding up rectangles over here, you can add up parallelogram areas over here and find the area under a region here by instead finding the region here and scaling it. That's the idea. So because Jacobian is the scaling factor, absolute Jacobian absolute value. The scaling factor between coordinate systems the following theorem results, which is the main topic for tonight.
So when you did the two graphs, was that like you basically deriving what the determinant is, or is that like the actual answer at the very bottom?
I guess I should say the area is actually the absolute value of AD minus BC. For linear transformations, it's a direct transformation from parallelograms here to parallelograms here. And so when you were adding up little rectangle subregions in the plane over here, you can equivalently add up parallelogram areas in this plane and the scale them to get, of course, value area in the other space. So here's the following result, and unfortunately, this is a very inexact translation. They don't want to cover all the cases, so I'll just state it the same. I mean, you hardly ever see this in mathematics, but it's an imprecisely stated theorem. They just don't want to state the special cases theorem. It says this: if x is a function of u and v, and y is a function of u and v, some coordinate transformation has continuous partials on region S in the UV space with image, all the points corresponding to that in XY space, phi of S equals R, such that the Jacobian of that transformation, and maybe I should put up here phi is the name of the map, phi. And then takes the region S in UV space to the region R in XY space, such that the Jacobian one that we wrote up there is of one sign plus or minus then this is where it gets imprecise, for a nice case, they just say for nice, I mean, they don't want to say what it is precisely. It's, for nice cases, let's say, the double integral, anything we're going to run into in this course will apply to it. You just want to avoid things like fractals and these pathological cases. The double integral of a function f of x, y, dA, and they're going to put a little subscript down here, dA x, y, meaning you're going to put dx, dy here, over the region R in xy space is equal to the double integral over S, whose image R is, in UV space. So you write f of x of UV, y of U and V, Jacobian. I'm going to write the Jacobian this way, dxy d UV. dA UV, meaning du dV or dV du. For appropriate integration limits. Technically, what these mean is the limit of the double sum there in both these cases, where you take rectangles in the one space and the rectangles in the other to add up the regions. Oh, and I forgot one very important thing. It's the absolute value. It's absolute value of the Jacobian. Have to be a little careful when you write this. Those straight bars on the matrix, it means determinant. But I write straight bars right here, it actually means absolute value. There's a confusion of notation there. Sometimes occurs. And it's because the absolute value of the Jacobian is the magnification factor. Now, even if you don't have a linear transformation like that, the linear transformation, this is a constant, and then you're just putting a number in here. For nonlinear transformation, still locally, what you get is rectangles in the one plane transforming into approximate parallelograms in the other plane. And so you can, the limit, you still get the same result with what happened. All right, so that's the big theorem, is that you can evaluate general integrals of f of x, y that maybe you couldn't do before under more general coordinate transformations. You have to have continuous first partials, and the Jacobian has to be of one sign. Can't ever be zero. Then you can evaluate it in this new coordinate system, where maybe these integration endpoints are a lot easier, provided you put the Jacobian in. have an example here. I haven't moved it too far. All right, so here's a really great example. This is a problem set. Suppose I wanted to evaluate this integral, x minus y e to the x squared minus y squared dA over some region R in xy space. And that region is bounded by x plus y equals 0. X plus y equals 1. X minus y equals 1. And x minus y equals 4. I suppose you're interested in evaluating that. This one is actually screaming for a correct coordinate transformation, if you think about it, because both the integrand and the limit points will be simpler if I just make a simple linear transformation. Using this theorem, let me just leave the conclusion of the theorem down here. So we'll sketch this space. X plus y equals 0. What is that? That's the equation y equals minus x. That's the line through the origin of slope minus 1, right? So here's y equals minus x. And then here x plus y equals 1. That's a parallel line, right? That's y equals minus x plus 1. It's y-intercept 1 and slope minus 1. This is y equals mx plus b form. So it goes through y equals 1, parallel to this line like that. Y equals, well, let's write the original form. This was x plus y equals 0. This was x plus y equals 1. And now we can do these others also. This is y equals x minus 1. That's slope 1 and y-intercept minus 1. So it's down here. And slope 1, so it comes up like this. X minus y equals 1. And then x minus y equals 4 is equivalently y equals x minus 4. So it's slope 1 and y-intercept minus 4. And now you can observe that the region is this right here. There's the region R in XY space. What a mess. Suppose you tried to evaluate this as a type 1 or a type 2 region. What would happen? You'd have to break it up into a top curve and a bottom curve right here. And then a top curve and a bottom curve from here to here. And then another top curve and a bottom curve here. So you'd have to do 3 different integrals, on top of which you've got this terrible integram that does not look like I can integrate it in the first place. Right, it's got that e to the x squared thing, which is I remember this one as a non-elementary integral. So how am I going to ever do this, right? But a coordinate transformation makes this nicer, right? Maybe. Here's the nice coordinate transformation. What we'd like to do is make it so that these angled lines become rectangles in the UV space, and then we'll have constant endpoints instead of these messy endpoints. That'll simplify things for starters. So let's make a change of coordinates. U equals x plus y. P equals x minus y. Or maybe they put it. That's what they did. Okay. Oh no, they did it the other way. They put yeah, u equals x plus y. Yeah, that's what they did. Okay. So suppose I make that change of coordinates. The first thing I need to do is evaluate the Jacobian, and alas, I can't, because to get the Jacobian, I need x and y written as functions of u and v. Fortunately, these are simple linear equations, right? U equals a number times x plus a number times y plus a number is a linear. And this one will lead to the following. If I want, why would I pick this? It's so that now these boundaries become u equals 0, u equals 1, v equals 1, v equals 4, constant endpoints is the idea. But now, alas, I have to find the Jacobian by finding the inverse transformation. So this change of coordinates has inverse. This change of coordinates is going to give us constant endpoints is the idea. It has inverse how? Well, we can just solve this in reverse. Since they're linear equations, we can solve them. If you've had linear algebra, you can solve them quite easily. Let's put them next to each other in case you haven't had linear algebra. Probably you haven't. That's one of the more important courses in addition to calculus when you're in college is linear algebra. I can add these two equations. If I call this equation 1 and 2, I can add this and get u plus v on the left equals 2x on the right plus 0. That eliminates y. That's the idea. I add these two to eliminate y. And this says that x equals u plus v over 2. There's the transformation going the other way. Similarly, if I take u minus v, that will eliminate x. So I'll take u minus v and take on the left equals x minus x cancels as I wanted, and y minus a minus y becomes 2y. And so I observe then that y equals u minus v over 2. So here's the transformation the other way from uv to xy, just by doing a little bit of adding multiples of one equation to another in general. Here I just had to add and subtract, but in general you take a multiple of one and add it to a multiple of the other, and you can eliminate a variable. Have you done that before? Right? I think we.
Like,
Yeah.
Substitution or elimination or something?
Elimination, yeah. And there's an orderly process in linear algebra called Gaussian elimination. You show there that every system of linear equations, you can always solve it or show that it has no solution. And so this process always works. That's the nice thing about linear equations. And so we get this transformation, x and y, and now I can find the Jacobian, right? I guess I have to rate my formula right before I need it. I always tell my classes, Murphy's Law is one of the things we learn in my class. Murphy's Law says that if anything can go wrong, it will go wrong. Murphy was an aerospace guy, and right in aerospace, you can't have anything wrong. You wind up blowing up the pilot or something, or you just can't. The satellite crashes, and it's a disaster. So anyway, so here we have Murphy's Law and the Jacobian, which we'll write this way: du xy at the top, duv. Is what? It's the determinant. We take partial of this with partial of x. Let's write out dx du, dx dv, dy du, dy dv. And actually, if you forget and put the x's and y's down and the u's and v's across the other way, it comes out the same number, so it doesn't matter. But this is the usual conventions: put x's and y's and then u's and v's. All right, so partial x with respect to u is 1/2 plus derivative v over 2 is 0, so you just get 1/2. Partial of x with respect to v, right? 1/2 u has derivative 0, 1/2 v has derivative 1/2. Partial of y with respect to u is 1/2, but partial of y with respect to v is minus 1/2. So there's the Jacobian, is this matrix. And it comes out a matrix of constants only because it's a linear transformation. Nonlinear transformations, there's variables in there, and the value of the Jacobian depends on what points you're at, but still locally it gives you the right magnification factor. So here we got 1/2 times minus 1/2, right? This diagonal minus the other diagonal, 1/2 times 1/2. Now it's a 4 minus a fourth minus a fourth is minus 1/2. So the scaling factor is minus 1/2. And now by the Jacobian theorem there. Oh boy, Murphy's Law again. Okay. Let's put it over here, I guess. I think we can still see the camera. By, did I call that number 2? I didn't give that equation number, did I, on the big theorem? By our theorem. That's the other one that needed a number. Should have given it number 2. By our theorem, the double integral that we have, x minus y e to the x squared minus y squared, dA, which can also be written as double integral x minus y e to the x plus y times x minus y. dA over the region R, this tilted rectangle, if you will, can be rewritten as a double integral over S, the region in UV space whose image this is, as, well, x minus y is just V, right? X plus y is U, x minus y is V, and then this was dA in the XY system, this is dA in the UV system. And so this double integral can be rewritten as this double integral. A little easier, right? Now I got rid of those squares. It's just e to the u times v. But moreover, it's a simple reason, because if we look at what these boundaries are, since we put u equal x plus y, this boundary becomes u equals 0. This boundary becomes u equals 1. Because we let v equal x minus y, this boundary becomes v equals 1, and this boundary becomes v equals 4. And so now this becomes the double integral over a rectangle in UV space. In other words, this is the image under this linear transformation of the region in UV space. U going from 0 to 1, and v going from 1 to 4. So this rectangle. So there's your S. This is the match V taking it over. And so now we have to integrate over S. All we have to do is let U go from 0 to 1 and V go from 1 to 4, because it's constant. It's vertical and parallel lines there. And I'll take V e to the U dV on the inside, du on the outside, since I put the limits for V here. Maybe I should do it the other way. Doesn't matter so much. All right, let's just leave it like that. And this is a lot easier one. This one I can do, right? Any questions on that so far that you want to look at? Well, that's the whole idea of the Jacobian. Just like polar coordinates and cylindrical coordinates and spherical coordinates made our double and triple integrals easier, we can make our own designer coordinate system that makes this one easier. Right? With the boundaries where these lines, we can make a new coordinate system in which these are constants, right? U and v equal constant. Integration endpoints are easier, and because this happens to be simpler in U and v, the integrand actually also simplifies. So you kind of have to still be a little lucky for this to work both for the integrand and for the endpoints. But you know, sometimes you get lucky. So, and sometimes even if you don't get real lucky, you can still make it easier, right? All right. So now we need to be able to evaluate this one. Remember, integration by parts can apply to the inside one. So I'll take this is going to be the integral from 0 to 1 du on the outside. And unfortunately, we've got u and v here, so we write integration by parts differently than. But the idea is you can, in integration by parts, call it u hat. This dv hat, and the integral u dv hat is u hat v hat minus v integral v to u. v hat du hat. Integration by parts. Perhaps to separate the letters. And if this is u, then du derivative of that is just 1. Boy, these u's and v's are really making it hard, aren't they? 1 dv. And if this is dv hat, then the integral of this is 1 over u e to the uv is v. So you integrate dv this to get v, and you integrate this, get d, or differentiate this to get du, and now you can rewrite this as integral from 0 to 1 of v times 1 over u. Well, I wish I hadn't used u and v now. It should be a lot of e to the uv. There's u hat v hat minus integral v hat du hat. So v hat is this 1 over u e to the uv. Du hat. Okay. So integration by parts gives us that. U hat v hat minus integral v hat du hat. This needs to be evaluated at the endpoints. V equals 1 and v equals 4. We've got integral from 0 to 1 of v over u e to the uv. Should have done this in the other order.
Could you just switch which variable you were integrating with respect to first, and then
Integrating with respect to v first. Yeah, maybe should have integrated with respect to u first, I think. I need to switch it up now, but I think it'd be a little easier. Yeah, let's do that. Let's integrate with respect to u first. Oh, what it was, my first instinct was right. I should have switched this, made it easier. Then I think I can avoid the integration by parts. All right, so let's switch the order, which we can do because it's just constant endpoints. Integral from 1 to 4, integral from 0 to 1, v e to the uv, du dv. And now the inside integral p is treated as a constant, so you can pull the v out and put it out here. So I can do it like that. Now I'll avoid the integration by parts. Integral of e to the uv with respect to u is e to the uv over v, right? Just treating v as a constant. This is e to the ku is e to the ku over k, but k is v. And that needs to be evaluated as u equals 0 and u equals 1, and then we'll integrate with respect to v next. I guess I'll avoid this nasty integration by parts problem. Now the v's cancel nicely also. See how it's a problem here? Even with the coordinate transformation, you still have to kind of cook it a little. All right, so you plug in u equals 1, and you got e to the v. You plug in u equals 0, and you get e to the 0, which is 1. So we need to integrate this. Now this isn't hard at all, right? Integral e to the v is e to the v. Integral of 1 is v. We're going to plug in 1 and 4 and take the difference. So this becomes e to the 4 minus 4 minus e to the 1 minus 1. is e to the 4 minus e minus 4 plus 1 is minus 3. So there's the value of the integral. In the new coordinate system, we were actually able to do it.
You said that if our bounds aren't constants, you can't flip the order of the integrals you'll take.
Except I botched this whole thing, right? Jeez, let's see. No, I didn't. I messed up on one thing here. I'm sorry, I'll get back to your question. I forgot to put in my Jacobian, which is the point of the problem here. You gotta catch me. This is not true here. What's wrong here? I left out the absolute value of the Jacobian, right? I need to rewrite this with the Jacobian. DAUV. Absolute value. Now the Jacobian was minus a half. This won't change the problem much, don't worry. And so the absolute value of the Jacobian is plus a half. And what you have to do is just put this Jacobian here and then put a half ever after. And this will all work out. So there's a half in here. I can pull a half out front. 1/2, 1/2, 1/2 times all this stuff. And I guess get all this stuff over 2. The question again, I'm sorry. I just want to make sure I fix that because that was the point of the problem, was put the Jacobian in there.
Did you say that we couldn't flip the order that we're integrating to if not all the bounds were constants?
Oh, not quite. I said because they're constant, you can interchange them. But yeah, that's true. Actually, if I have this a function of u here, like this, maybe u squared or something, I can't interchange them because I would have to, right? This is a function of, because the endpoint depends on u, I can't interchange the order. Right, if I try and pull this integral sign inside here, the u comes outside the integral. So you can't take u outside the integration over u. Yeah, so yeah, you can only interchange the order like that. If the outside ones are always constant, but you only interchange the order if the inside ones are also constant. All right, so this had a magnification factor you had to put in there 1/2 because in the UV system, the areas were twice as big as in the XY system, so you had to multiply it. All right, well, if you can do this in the 2x2 case, you can also do it in the 3x3 case. In other words, you can do it in 3 dimensions. So similarly, for coordinate transformations in 3 space, you can give it a letter if you like. Phi makes x a function of u, v, and w, y a function of u, v, w, z a function of u, v, and w, with continuous partial derivatives. The Jacobian is a 3x3 determinant. Maybe some of you have seen this before, which we can write J again to save writing, or we can write more suggestively d x, y, v, z, d, u, v, w, like that. is this 3x3 determinant, dx du, dx dv, dx dw, dy du, dy dv, dy dw, dz du, dz dv, and dz dw. Where the 3x3 determinant is actually harder. It's enough harder that I'm going to index it a little differently. Instead of putting A, B, C, D, I'm going to write it like this: A11, A12, A13. Suppose this is your an array of numbers, number. They're just indexed this way. Here's another number: A21, A22, A23. And a rectangular array of numbers like this is called a matrix. But if you put bars on the side, we call it the determinant of the matrix, and it's just a number. So the array of numbers is a matrix. When you put these bars on here, it doesn't mean absolute value. It means do this to it. There's different ways to define this. One way, and the most popular way, is to say, well, it's this number in the upper left-hand corner, A11, times the subdeterminant gotten by wiping out its row and column. These four numbers, A22, A23, A31, A32. And we already know how to calculate 2x2 determinants, right? It's just this times this minus this times this. And now what we do is we take the second row in the first, second number in the first row, but this time we subtract minus A12 times its subdeterminant got by wiping out its row and column. Then we're left with these four numbers, right? If we wipe out the row and column. So A21, A23, A31, A33. Then we add the last element in the first row, A13 times its subdeterminant gotten by wiping out its row and column. A13 times, wipe out its row and column, now you have this matrix left, you take its determinant. A21, A22, A31, A32. There's the definition of the 3x3 determinant.
For the first one, bottom one being.
Oh, yeah, I just wrote it, didn't I? Yeah, I said it's this part. Oh, no, that's right. Yeah, let's see. But for the first one, it's this four. Wipe out the wrong column. 2, 2, 2, 3. I had that right. And then 3, 2, 3, 3. Yeah, geez, I miswrote it. 3, 2, 3, 3. Wipe out the row and column of the first row element. And you might say, why do you have to use the first row? Why define it that way? The fact is you don't. You can also take the first column. This one times its subdeterminant minus this one times its subdeterminant plus this one times its subdeterminant. It comes out the same. You can expand it on the third row the same way. This one times its subdeterminant minus this one times its subdeterminant plus this one. But if you do an even row, then you have to take minus the first one plus the second one minus the third one. So you can actually expand on any row or column. It's just if you use an even row or column, then you go minus plus minus instead of. So in linear algebra, you get into detail and all that stuff sometimes. Sometimes that's so detailed you don't bother. But determinants can be expanded on any row like that. And there's other ways to define them too. But that's the most popular way. Some people really like something that was pioneered by one of those famous physicists. I can't remember which one. I don't know, Oppenheimer or I can't. Came up with this thing called the no-peeking method, where in order to keep track of all those things where you're trying to imagine wiping those out and put these left and wiping those out and leaving these. He put it down like this: A11, A12, A13, A21. You'll see this in some books. I can't remember if it's in yours or not. A31, A32, A33, and then you copy the first two rows again, first two columns again, A11, A21, A31, A12, A22, A32, and then it's easier because you take this one times, right? this times this minus this times this, then you take this one times, and you just take this one and this one times these, and so anyway, he's got a method of, you know, doing it that maybe saves a little bit of that, trying to, if you got dyslexia or whatever, trying to figure out what's what. So you can see this online if you Google it for evaluating determinants. All right, so suppose we do the 3x3 determinant. Here's my favorite one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose I put the first 9 numbers into a determinant. I wonder what that comes out to be. Well, you take this one, 1, times the determinant got by wiping out its row and column. So it's 5, 6, 8, 9. Then you subtract this one, 2, times the determinant got by wiping out its row and column is 4, 6, 7, 9. Then plus this one, 3, times the determinant got by wiping out its row and column, 4, 5, 7, 8. And let's see, now we know 2 by 2 determinants is 5 times 9 minus 8 times 6 minus 2 times 4 times 9 minus 7 times 6. And then plus 3 over here times 4 times 8 minus 7 times 5, diagonal minus diagonal, right? And we come out with 45 minus 48 is minus 3, minus 2 times 36 minus 42 is minus 6. And over here, plus 3 times 32 minus 35 is minus 3. And I've got minus 9, minus 3 more is minus 12, plus 12 is 0. So this determinant comes up to be 0. And guess what? If you have this for your Jacobian, the theorem would fail, right? The Jacobian has to be of one sign, either positive or negative on the whole region, for that theorem to work. So this, and what happens is, if the Jacobian's 0 anywhere, you have problems with invertibility of the coordinate systems. You might be mapping a rectangular region into a line in the other space or something like that. So that's what's going on there. You can't, typically you can't invert the coordinate system to go back and forth from one region to the other. But there's an example of computing a 3x3 determinant, just not a good one for doing these coordinate transformations or for doing these theorems. Now the same theorem applies in 3 dimensions. So similarly, I guess we should write it down. In 3D, if the coordinate transformation with continuous partials has the Jacobian with this 3x3 determinant of one sign, either positive or negative on the whole region. We'll say on a nice region, not one with a fractal boundary or something. With nice integrand. This means almost always, it's pathological cases. What you can do is take the triple integral over the region R in XYZ space, and now you've got a map like this. X, Y, Z, and you've written X as a function of u v w, we said. Y is a function of u v w, and Z is a function of u v w. And there's some region over here. I'll call it R again, although the book may change letters for the three-dimensional region, I can't remember. And here's UVW, we'll just give it the same letter S, and maybe some other nicer region over here, maybe a constant endpoint, so it's a rectangular block, who knows. And so you've got this map here, phi, given by some equations, maps UVW space into XYZ space. That's the idea. Then this triple integral of f of x, y, z, dv, meaning the limit of the sum of rectangular parallelepipeds in UV in XYZ space, can be written as the triple integral taking rectangular parallelepipeds in the UVW space over the region S, whose images are f of x of UVW, y of UVW, z of UVW. Absolute value of the Jacobian again, d x, y, z, d UVW, dv UVW, adding up, right, the limit of the triple sum of rectangular parallelepipeds in UVW space. That's the big theorem. It's the same one, just with a 3x3 determinant and triple integrals. And then we can make a note on this notation. Why is that kind of a neat notation for Jacobian? These are generalizations of the substitution theorem from calculus 1. That's all they are. Once you think of it that way, this all makes a whole lot more sense. In calculus 1, what you did was you said, use substitution. If I had an integral f of u of x du dx dx, I should write it the other way. It's usually written this way. Let's write it backwards. F of x of u dx. I could rewrite this as an integral in over whatever interval I in along the x-axis. I can maybe I should call it R just to be consistent, even though it's not a region. You can rewrite this as f of x dx as integral f of x of u x du u by u substitution over s, where R is equal to image of S. So the u substitution theorem is written sort of backwards here from the way it's usually presented. Integral f of x dx can be written as f of x dx du. I usually go the other way, but written this direction, what we get instead is that the integral over a plane region, f of x, y, dA, think of dx dy, becomes the double integral of f of x of uv, y of uv, and instead of putting dx du, we put the absolute value of the Jacobian, dxy duv, du dv, and so the Jacobian is just replacing the dx du you wrote here. And in 3 dimensions, similarly, the triple integral over the region, or more generally solid. I think they use G for solids, but At the risk of a faux pas in letters, I'll still call that R. F of X, Y, Z, dz, dy, dx can be rewritten as a triple integral. F of, just what we wrote there, X of u v w, Y of u v w, Z of v w, u dv dw or dw dv du. Provided you put in here the absolute value of the Jacobian as a magnification factor, d x y z p u v w. Now, what is this thing? If you do a linear transformation, this actually is, this turns out to be the area of the parallelepiped, which you do in terms of the cross product and dot product. We could say also that for a linear transformation, where you just use numbers times the variables, so it's x equals a number times u plus a number times v plus a number times w. Y equals a number times u plus a number times v plus a number times w. Z likewise. The Jacobian absolute value is this determinant, just the one we showed there, A11, A12, A13, A21, A22, A23, is a constant, right? Because there's no variables on it. These are all just numbers. Is the volume of the parallelepiped. Because for linear transformations, it transforms parallelepipeds into parallelepipeds. This is absolute value. This one here means absolute value, and this one here means determinant. So that maybe I should put absolute value here. But those two get confused. When I put it on this one, it means absolute value. This means determinant of the numbers inside. So this is absolute value of this one, of this determinant, is in the volume of the parallelepiped, corresponding to the 1 by 1 by 1 region in UVW space. So it takes a 1 by 1 by 1 cube in the one space and makes it up into this volume, and so that's the magnification factor between the two coordinate systems. Well, I'm about out of time. I didn't get to everything tonight. Well, I guess I'll have to quit it right there, and then I'll give you the list of problems, but we haven't quite finished them all. I guess we'll finish them next time. I gave you the ones out of 14.6 last time, right? Thank you. I think it was 19 odd, I think. Out of 14.7 on the Jacobian, we'll look at some of these with 3 dimensions next time, but you can try the ones in 2 dimensions where you're transforming plane regions into plane regions like we did. We need to do one more example of that too, but 1 to 15 odd. Then 21 to 23, all of them. 31 to 35. To do eventually. Yeah, I'm still coming back to surface area. I'm finishing up the volume integrals and then coming back to surface areas afterwards. We'll do it. All right, so I hope that was kind of fun, and it really shows you that you can make quite general coordinate transformations. Try and make your integrals easier. The Jacobian is actually a very important topic in coordinate transformations and other subjects too. Try to keep the Jacobian non-zero. What you want to do so that you get into vertical coordinate transformation.